Okay, so hello everyone. Today we will be discussing this research paper, HyperFast Instant Classification for Tabular Data. Okay, so as the name is suggesting, HyperFast is something related to speed, fast word, great. So, and this is solving the instant classification problem for tabular data. Okay, only the classification problem for tabular data. This is what related to this. Great. So in the traditional machine learning method or whatever method we currently use is uh, we have a data set, we have a model. First we divide it into training and testing, and then we train our model, and then we do the testing. So while training, it takes some time, it takes some resources on the GPU, on local whatever CPU you are using. So basically it takes time. Obviously you have to train your model to give to for the inference or to generate response or for the prediction, you can say. But here what we are doing is, here we have some kind of model you can think of. We have already have a trained model, and you have a classification problem. So what we are doing is, we are just asking this model to solve this problem directly. Already we have a pre-trained model. Okay, so the problem arises is, how do we have such we can have a different types of classification problem. No? Let's say I am classifying dog, cat and dogs. I'm classifying health, something related to health. I'm classifying something related to uh, the this is a male or female, something. There are various classification problems. So how will be things will be difficult na, to have a certain like architecture or model to just give me the answer. So what we are here doing is, main thing is, we are keeping a meta trained hyper network. Just think of a pre-trained model, like a pre-trained architecture, pre-trained model. So it is already trained. So what we are here doing is, we are using that pre-trained model to generate the weights. Okay, so whenever we are solving my problems, whatever your end goal, we just need a function to relate the input to output, like to the x train to the x to y train, to the data to the labels. Okay, so we just need the theta, weights and biases. We only need the weights and biases, parameters. Those are the things. If we have those, we can just get the answer. So here, using this pre-trained model, we will be getting these parameters, these weights and biases. So these thing is the most important. Okay, there's written something here. Mm, 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 mm. Great. So I'm just repeating again. So this method, hyperfast, it is a meta train. Think of it like a pre-trained hyper network. Okay, is also a network, just different kind of word. We'll discuss in detail what is the difference between those hyper network and network. Okay, solving the instant classification of tabular data. Great. Okay. Okay, what I wanted to show, meta sample model on hyper. Okay, let's walk by line by line. Okay. So here it is saying that, traditional methods like gradient boosting and remains good choice for tabular data. Okay. So here we are using the pre-trained meta-trained hypernetwork for instant classification of tabular data in a single forward pass. Okay. So we will use this meta-trained hypernetwork to get the parameters, like to get a theta for our neural network, and will use that theta, use that theta or those parameters to just get our answer, to get our classification, like what is our class for this problem. Okay. So hyperfast, this is the great thing. Hyperfast generates a task-specific neural network tailored to an unseen dataset and can be directly used for classification inference, removing the need for training. And this is the only two lines required for the paper, like overview of the paper. Okay, so we have the pre-trained meta-trained hyper network for doing instant classification in a single pass. Great. What we're here doing is, we are generating a neural network, we can say, or all the parameters in each layers. Great. Tailored to the unseen data, since we are passing the data set. Of course, obviously the model won't be trained on that data set, and it will be giving us the neural network, so which can use it for our classification inference. Okay, and we are not training here. Are you getting my point? That, like, we are not training the model. We already have some pre-trained hyperfast model existing somewhere, and we will solve the problem. We'll just import the weights, and we have the architecture. and directly we can pass our this unseen or new data set and get a result. Okay, you're saying that HyperFast is a strong solution for numerous application and rapid deployment, modern deployment pace for the fast deployment process. This is very good, great. And they got same thing, a novel method to solve classification tasks from multiple domains with a single forward pass, a single step. Okay, there's a similar method called PFN. So so instead of using a meta-trained hypernetwork, it used a pre-trained transformer. Okay, but there was a constraint like uh, we can only use less than 1000 training example here, and this one 100 features and 10 classes. Okay, okay. This was just explaining that part again. We already have like while in inference stage, we already have the hyperfast, and we will receive a support set. Support set will simply the data set will pass like on the X train and Y train part, and there is with the prediction which classifies the test of the sample. Okay, okay. Okay, we can also use ensembles, assembly method, like assembling multiple, let's say, using this what we are doing, we are just generating some parameters. We can do this process for multiple, let's say 3 times, 5 times, and then we can ensemble or just get the best of or average of the result. Can't say, we can say the average of the prediction and then we can select the best average. Okay, great, best prediction. Oh, this is inference, great. Okay, so this is explaining what is actually a hypernetwork. So hypernetwork is one neural network is used to generate the weights for the network. So this is the most important part. Okay, we are saying okay, there's two terms: meta learning, hypernetwork. So for written here, hyperfast is a meta trained hypernetwork. Okay, so what is meta train? Meta training is basically the approach na learning to learn. Okay, and hypernetwork synchronization, we have already have one neural network. Simply we already have trained this, and using this trained neural network we are generating the weights for another one. Okay, so this is the weights for our current problem, and this is the generic hypernetwork or network we have already trained or already existing somewhere. Okay, when we solve a problem we just import this, import the architecture and the weights. If we use, let's say you want to use any transfer learning, simple thing, we already have the model uh, architecture and the weights, we just import it and run for our current use case. But those are very specific, they are already trained for, let's say, uh, object detection or localization part. But here it is very generic, no? Our classification problem may vary, so this part is very interesting. Okay, this is basically the case of transformer. Okay, okay, great, great, great. Okay, just saying our hybrid design includes initial transformation module. Okay, we'll discuss this. Different pooling operations in architecture. Okay, and this offers feature permission variance. Okay, scalability and adaptability to your new data set. Okay, I have to pick up the page. Meta learning. Okay, so these three methods were very popular for XGBoost, like SGB and CatBoost for tabular data. Okay, attention hyper fast. Okay, so let's just go into the architecture part only. Okay, so you're seeing these are support samples, they support labels. So this is the kind of pre-processing part. If you standardize the data, standardize means you should perform one-hot encoding of the for the categorical feature. Great. We impute the missing numerical features by mean and the categorical features by mode, and there's also the feature wise transforming to zero mean and unit variance. Great. Okay, so this part is done. Then we initialize random features, and there are random features. Okay, this part is very important. So we use random features here. So what we do is how it is calculated. So this part is important. We use A is a kind of non-linear transformation type of thing. Okay, and W is a some matrix. Okay, so we use a random matrix W, and we did a matrix multiplication with our input. Okay, and there is a nonlinear transformation. Let's say ReLU, leaky ReLU, and tanh, all the transformation like we did a neural network. Okay, so W into X into this is nonlinear transformation. Great. Okay. Okay, from here we approximate the kernel, whatever kernel we were using. So here we prefer arc cosine kernel. Okay, so the reason we gave was it captures neural sparse neural network like feature representation and okay, non-parametric concept. Okay, we are not using training for weights here. Okay, great. Okay, this part is okay. You've used PCR. Okay, so what is the quick overview here? Let's say we got our data, we standardize it. Okay, so here, okay, what is the problem is now? We have a generic trained model, but say let's say we have a classification problem. It has 100 rows, and next one has 200 rows, third is 300, 500. So we won't have a fixed input sample, a fixed input size. So we need to do something like we need to make it into a fixed size. Okay, one of the reason is that also we need to like there was a term in okay I have to check it, what is called invariance. Okay, you will read it here, you can check, go through it. Okay, so make things better. So first it basically expands the our data to a higher dimension to about 15 in order 14 15. Okay, then we type of compress it using PC, simple dimension reduction technique. Okay, great. So here hyper network includes concatenation of labels, average pool per class, and this one. Great. And from hyper network we get the weights of our linear like the current model, which will be no weights of the kind model. For kind model, uh, solving the kind problem. Great. And also we use nearest neighbor to it is basically added from this part plus this part to make our results like a bit better. Okay, so when we get our rates of a linear from hypernetwork, so there is also share module between them. I won't go much into that. Okay, okay, so this was a deep set. Okay, so basically I was doing average this part, average pooling here. mm, these are the experiments. I compared it with AutoML, autoglucons, and okay, great. Okay. Data, we get data from sample set. Okay, various sources, spread of 25, 10, 15. This was the result. Okay, we can see here. All this is the probably hyperfast. Balance accuracy we got was much better compared to the other KNN, XGBoost, CatBoost, AutoGluon, other methods. Okay, so this was a time with like respect to time. So here we also see average balance accuracy rank. Okay, great. Okay, this was the part. Random features we use. We set random features to like 2 to 15 features. So basically, when we get output, we kind of expands it in this space, random feature space, you can say, and then we use PCA, visual component analysis PCA. Okay, so then we compress it into 784 uh, components. Okay, so there were other choices too later in the application study. We'll check it out. Okay, so here was when we clip the data for outliers for this operable data set. Okay. So basically they did two kind of study for small size and medium or large size data set. So here is the ablation study. Basically first removed RF and RFPCA. So things were not accuracy basically reduced. Oh, sure. One more part, what is balance accuracy? So balance accuracy is basically the mean of sensitivity and specificity. Sensitivity is just a recall, and specificity is basically uh, how many false positive you are actually getting, like you are actually correctly reporting. Let's say uh, let's say you're having classification problem to determine how many cancer patients are there. So specificity will be how many non-cancer patients can you actually determine, like model can actually determine specificity, and this will be for the cancer patient. Are you getting my point? This is the recall, and this will for the negative part, true negative ratio, you can say true negative rate, and this is true positive rate. Okay, results or analysis study conclusion. Okay, let's just move on conclusion. Okay, so yes, we compared with the state of what ML, auto ML, which was trained for 1 hour. Okay, so our method HyperFast was performing better than that. And okay, so basically, and if we can improve here, we all work on tabular data, but if you want to improve it, we can go for handling regression tasks and other non-logical like audio, 3D, video. Great, great, great. And so there was a residual connection in both the hyper network and the main model. Okay, so this is a kind of quick review of the paper. I was not able to understand the paper 100%. Oh, obviously, it was around, I will say 50-60%. Okay, when I will come and go through the paper later in future, maybe things will improve. And there was also experimental setup discussed later. So it was here it was saying that in the gate and steps when we use a single for each iteration, the things are very noisy, so we kind of accumulated for the 25 steps and we checked for various steps and 25 was better. Okay, okay. And you are solving multiple problems in a single pass, but this was not great, facing memory constraints. Again, for when the hyperfast is trained, we have already meta trained hyper network. Okay, so we can just keep the weights frozen and just take it to use all solve our classification problems. There is much more. Okay, for hyper tuning, we use hyperopt here. Okay, Python library using Python optimization. Things are much more. Yeah, you can just go through over it. Okay, then bye bye till then. Okay, let's we just add a limitation part. Okay, so the main focus here was a simple yet effective method suitable for most stable data set with constrained computational environment, like time constraint and resources constraint. This part was very important. Okay, so here we all work with up to 100 classes. If we want to make it better, we can go for it. Look, obviously the computational requirement will be more. Computational requirements will be more. Great, yeah. That's it for today. Bye bye.